Alright, so today we're looking at flow proofs, which uses arrows to show the flow of the logical argument. So basically, if you know what a flow chart is, a flow proof is basically a proof in the format of a flow chart. You're going to have boxes and arrows showing what's connected and what goes where in what order. Alright, and then each reason in the flow proof is going to be written below the statement it justifies. So you'll have a box with the statement in it, and then the reason goes below it. And so we're going to start off today by doing a simple proof that we have done multiple times already this year. And so we should be able to go through it fairly quickly. So given that AB equals CD, prove that AC is equal to BD. So we're starting with AB and CD, these two small segments, and we want to end up with AC, which is much bigger than AB, and BD, which is much bigger than CD. So we're starting with small ones, and we've got to make them bigger. So we're going to have to add something to them. So first step always is the given, which is that AB equals CD. And then from there, since we want to go from AB to AC and CD to BD, we've got to add something to both of those. And to go from AB to AC, we've got to add this big chunk of BC. And then same thing to go from CD to BD, we also have to add BC to CD. So since we're going to add BC, we need to bring it into the proof to start off with, saying that it is equal to itself by the reflexive property of equality. And our whole purpose of entering it in there is because we know we need to add BC to AB to make this section that will ultimately be AC, and we need to add BC to CD to make this section that will ultimately be BD, which is where we're trying to get to, AC and BD equal to each other. So then from there, we're going to actually do what we brought BC in to the proof to do, and we're going to add it to both sides of AB equals CD, which is the addition property of equality. So anytime we add the same thing to both sides, maintaining the equality of the equation, that is the addition property of equality. So AB plus BC equals CD plus BC. And we've done that because we know that AB and BC added together is going to equal AC just by looking at the picture here. And we also know that BC and CD added together is going to equal BD. But we have to actually explain that that's what we have coming into the equation. So our next step is we're going to use this picture and the segment addition postulate to show what each one of these things is made up of. AC is actually AB plus BC, and BD is actually BC plus CD. So that's the segment addition postulate, where we're showing that two small segments can be added together to equal a bigger segment. And so now from there, once we have this step, we can see that we have AB plus BC here, AB plus BC here. So since that's equal to AC, we can replace this AB plus BC with AC. We can replace this CD plus BC with BD. That's what it's equal to. And when we do that, we'll get ourselves to the point where we're trying to prove. And what reason would we use if we're replacing one thing with something else that it's equal to? Substitution property of equality. give us AC equals BD. All right, so this is what we call a two-column proof, right? It's a set of numbered steps in two columns. Another type of proof that we've done in the past is a paragraph proof, which just takes all of these steps in the same order, but then writes each one of them as a sentence in a paragraph form. Right? You have to add some transition words and whatnot to make it make sense and sound appropriate. But basically all it is each one of these steps written as a sentence. And when we do that, we'll get this paragraph proof that about to pop up too. Anybody still copying this slide? All right. All right, so here would be the paragraph proof, right? Exact same steps, but written as sentences. So just like any proof, we start with the given, right? We are given that AB equals CD. So first step, given, just like any other proof. Then we do the same thing as we did in the two-column proof. We next bring in the section BC, saying it's equal to itself, so that we can plug it into the equation later. Right? Using the reflexive property of equality, we know that BC is equal to BC. And then we take that BC and we add it to both sides of the equation. By the addition property of equality, we can say AB plus BC equals CD plus BC. So same steps, same the first three steps. Fourth step, the segment addition postulate allows us to say that AC equals AB plus BC and BD equals CD plus BC. All right, so just explaining that the AB plus BC is the same thing as AC, and the CD plus BC is the same thing as BD. And then wraps it up with a nice little therefore, AC equals BD by the substitution property of equality. So, really and truly, a paragraph proof is pretty easy to write if you have the two-column proof already completed. A little more difficult if you're coming up with it from scratch. And that will bring us to the third type of proof, the new proof we're learning today, which is a flow proof. So we're still doing the exact same proof, we're just doing it a third time as a flow proof, so we can see all three formats of a proof here. So, with a flow proof, just like any proof, we're going to start with what? What we're given, the given part, which is AB equals CD. A little box. You can put it in a circle, whatever shape you want to choose for your flow proof. And then underneath it, we're going to write the reason, which AB equals CD came from the given. Now then, one thing about a flow proof is we want to connect the parts that are connected and show if we start with one thing, then we draw an arrow to connect it to the next thing that it created. And so our next step was that we used BC equals BC with the reflexive property, right? Now, we did not get BC equals BC from the given information. We actually get that BC equals BC from the picture. Right? We're saying that this section BC is equal to itself. So it's not coming from the given. So it's not going to be connected to that box with an arrow. We're just going to draw a new box for BC equals BC. Write the reason, the reflexive property. Of equality. Now, step 3 is where we actually add BC to both sides. All right, we get AB plus BC equals CD plus BC. So that step is actually going to be made up of both of these steps going together. All right, we're adding the BCs to the AB equals CD. So when we build that, actually draw arrows from both of those boxes. AB plus BC equals CD plus BC. And the reason was the addition property of equality. All right. So the next thing we did was we used the segment addition postulate to explain what AB plus BC and CD plus BC were, right? Now, when we're using the segment addition postulate, we're not using this equation, we're actually using the picture and the segment addition postulate with the picture to come up with that AC is actually AB and BC added together, and BD is actually BC and CD added together. So we're going to write that as AC equals AB plus BC, and BD equals CD plus BC. And that once again is the segment addition postulate. So now we're ready to make the last step, which, remember, the last step just replaces AB plus BC with AC and CD plus BC with BD. So in order to do that, these two steps have to work together. These two parts come together to use substitution to create our new step. AC equals BD. By the substitution property of equality. All right. Questions on that? I think a flow proof is a little more difficult than the others because you have to actually determine what goes with what and in what direction do the arrows go. So, but you just have to ask yourself at each step, do I use the information in this step to create the next step, or does that information from the next step come from somewhere else? So you know whether or not you're drawing an arrow to it, or if you're just making it its own new box to start off with. All right, so that is a flow proof. We won't do a ton of those in the future. There will be one on the homework, but the standard form of a proof, what we'll see most often, is the two-column proof. Right? These are just different options on how to present the same material. All right, so now we got 3 different theorems to cover. All right. Theorem 3.1 tells us if 2 lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. Which, what do we know about the linear pair angles? What's their measure going to be? 2 angles in a linear pair. They're going to add up to 180. They're supplementary, right? So if I have a set of linear pair angles and they're congruent to each other, right? Remember these little tick marks right here are telling us that this angle is congruent to this angle. And so if those two angles are congruent and the total is 180, then if you divide 180 by 2, we get what? 90. So that means that it's a right angle there. And therefore, it would be perpendicular because they'd be intersecting to form a right angle. All right, theorem 3.2, if two sides of two adjacent acute angles are perpendicular, then the angles are complementary. Which should make sense because if I have two angles that make a right angle, the whole term complementary means that they add up to 90 degrees, and a right angle is 90 degrees. So if there are two angles that make a right angle because they're perpendicular lines, then they are complementary as well. And lastly, theorem 3.3 takes the definition of perpendicular lines just a little bit further, because the definition tells us that there's two lines that intersect to form a right angle. Theorem 3.3 goes ahead and says there's not just one right angle there. If you have perpendicular lines, all four angles at the intersection are going to be right angles. So, taking that information, and then one more proof. And this proof, we're given that segment BA is perpendicular to segment BC. Remember, that's what the upside down T says, it's perpendicular. And we want to prove that angle 1 and angle 2 are complementary. So basically what we're doing here is we are taking theorem 3.2 and we're proving that it actually works. Which is unfortunate because if we weren't proving that 3.2 worked, we could actually use it as our reason here and solve this proof in like 2 steps. But instead of using it to prove it, we're trying to use the proof to prove that theorem 3.2 actually works. So, if two lines are perpendicular, what do we know about those two lines? We'll start off with putting the given. And since those two lines are perpendicular, what do we know about the lines? Oh, that's what we're trying to get to, that they're complementary. But just them telling us that they're perpendicular, what other information does that give to us, knowing that they're perpendicular lines? They're going to intersect to form a right angle, right? Because that's what the definition of perpendicular lines says, right? Two lines that intersect to form a right angle. So that's what we're going to use as our reason, is the definition of perpendicular lines. And we're going to say angle ABC is a right angle. Because if they're perpendicular lines, they have to make a right angle. Now, there isn't another piece of the given to go back and get, so we've got to keep building our information one piece at a time here. So if angle ABC is a right angle, what else do we know about angle ABC? What does it mean for it to be a right angle? It's 90 degrees. And what's going to tell us that that right angle is 90 degrees? Anybody know? It's actually the definition of a right angle. If we look up the definition of a right angle, it's going to say an angle with a measure equal to 90 degrees. So now that tells us that this whole angle right here is a 90-degree angle. We're trying to prove that 1 and 2 are complementary. So what we have to prove is that 1 and 2 added together are going to equal 90 degrees, right? So if I look at the picture, ABC is actually made up of angle 1 and angle 2, right? So from that picture, I'm going to say that the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle ABC, which is just the angle addition postulate, saying that I can add two smaller angles together to equal the size of the bigger angle. All right. So now our goal is still to show that 1 and 2 added together is going to equal 90 degrees, which at this point we know that 1 and 2 added together equals the measure of angle ABC. And step 3 tells us what about the measure of angle ABC? Tells us that that measure is 90 degrees, right? So I can replace the measure of angle ABC with 90 degrees. And when I do that, well, what property is that if I'm replacing one thing with something it's equal to? Substitution property. So now I've got the measure of angle 1 plus the measure of angle 2 equals 90 degrees by the substitution property of equality. And since the measure of 1 plus the measure of 2 equals 90 degrees, what's that tell us about angle 1 and angle 2? They're complementary by what reason? Anybody know? What tells us that if two angles add up to 90 degrees, they're complementary angles? It's not a theorem. Definition of complementary angles, right? If I look up that definition in the glossary, complementary angles is going to say two angles whose sum equals 90 degrees. So angle 1 and angle 2's sum equals 90 degrees, so that means they have to be complementary. Questions, anybody?